Well, thank you for having me here. I'm Monica Beckwith. I'm going to talk about, like you said, about garbage first, garbage collector. Uh, why it's important? Because it's a new collector. There's some differences, and it's going to be the default collector in Java 9, like Christian mentioned. Another thing to know about G1 is that I think the framework, the regionalized framework of G1 is the future. We have seen regionalized framework from IBM. We've seen regionalized framework from Azure. And then this is OpenJDK, Oracle's regionalized framework. And I think it's going to be the base of even the throughput collector in near future. So I think it's going to be the throughput collector, and then it's going to be the G1, which is more optimized towards latency, is what my thought is for the future. A little bit about me. I'm Monica Beckwith. I have been in Java, JVM, GC Performance. I've done this for more than a decade now. I started at Advanced Micro Devices as a compiler engineer, static compiler, GCC, and then moved on to, they were building a team for Java Performance, and I was one of the first ones to join. I got to take a pick. There was the Sun Hotspot, there was the J-Rocket, and there was the IBM J9. So I picked Sun Hotspot, and I was lucky, I guess. I'm here right now. So right now I do I'm a consultant, and I consult with managed runtimes running on the JVM. My last position at Oracle was G1 GC Performance Lead. Okay, so let's start. So this is the agenda. I'll talk about why we need G1. I'll talk about the regionalized heap, the difference, the main difference in G1. We'll talk about humongous objects when I'm talking about regionalized heap, because this is something that people need to know with respect to G1 and with respect to the incremental compaction and how humongous objects may impact it. And later on, when I'm talking about tuning, I'll revisit humongous objects again. I'll talk about additional data structures in G1, which are called the collection set and the R set, remembered set. Then we'll move on to the phases of G1. If you know hotspot GC, you know that all hotspot GCs are generational. What that means is that you have young generation where new objects are allocated, or most new objects are allocated, and then promotion happens after aging them appropriately in the survivors. So we will always see, with respect to hotspot GCs, we'll always see young collection and old collection, okay? So in G1 also we have young collection, and then we have something known as concurrent marking phase. So once the old gen occupancy, actually the entire heap occupancy, crosses a threshold, which is called a marking threshold, it goes into concurrent marking, and that's where it identifies potential objects that need to be, or potential regions that will be collected from the old generation. So after the concurrent marking is completed, that's when we move to the mixed collection, which is also known as the incremental compaction or incremental collection. Why is this important? Because this is the first time any hotspot GC has an incremental compaction. So if you know the throughput GC, old generation is collected in a monolithic way. Basically, the entire heap is marked, swept, and compacted. Yes, you have multiple threads, but it's still monolithic. CMS does not do compaction. It does in-space deallocation of the old generation. What that can do is it can lead to promotion failures, concurrent mode failures, and eventually you'll have a serial, stop the world, compacting collection. Again, monolithic. So with G1 GC and with the introduction of regions, it's easier now to have something known as incremental compaction. So you don't need to collect the entire old generation. You can do it in an incremental way such that you're collecting you're identifying and then collecting the regions with most garbage. We'll talk about that. And finally, I'll talk about tuning. So again, with G1 GC, if you have been using hotspot GCs for a long time, you've probably been used to tuning it a lot too. With G1 GC, my advice is that if you know the defaults, if you understand the working, try to let the defaults work for you. This tuning that that I'm going to talk about is when the defaults don't work, when you have an evacuation failure, when you see some kind of wasted heap space, like internal fragmentation or something. So we'll talk about that then. Okay? Why G1 GC? Uh, so the next slides are something that I've presented to a big audience, and I hope you guys will enjoy it too. So a long time ago, in a galaxy not so far away, garbage first, garbage collector, and I hope this audio works. Okay. So we can dance now. So JDK 6, A New Hope. In a JDK 6 update release, a new garbage collector called Garbage First was introduced, but it wasn't officially supported until JDK 7 update 4. All testing with this new garbage collector seemed to show that it was ready to take over as the default collector. In JDK 9, this new collector has provided hope to restore scaling and predictability to the galaxy. Okay. All right, now moving on to why, if you ask me to come up with 5 points, why do you think you should try G1? I would say, first of all, G1 is considerate to your pause time goals. What that means is that previously also, so max GC pause millis is an option that was available since throughput collector, I think, and that was used to kind of figure out the throughput goal and kind of help with that. But really, G1 is built with that in mind. So G1 has adaptive sizing already in its algorithm, which helps with prediction logic. What that means is that if you tell G1 that I want a throughput goal of 200 milliseconds, G1 will try to adjust its generations and look at the previous pause times that it has been able to achieve and be able to predict what the next pause time is going to be. It's not a hard stop. So if you are at 200 and you are going, it predicts you're going to cross it, it's not going to stop collecting. So it's called a soft pause time goal. It also has a frequency, and I'll talk about that. There's also a frequency goal that means pauses as your application is working. Of course, the regionalized heap. We have to talk about the regionalized heap. Again, it's the future. Helps with now. So previously, your unit of collection was a generation size, right? Because it was monolithic. So your entire generation was collected. That's your unit of collection. With regionalized heap, your unit of collection is a region. So you can micromanage up until region, until the size of the region. Incremental compaction, I already spoke about that. Concurrent and parallel marking phases, which is cool because sometimes, previously, I mean, even here, you have the remark phases that are stop the world, but there's work done to make sure, so that there's a new concurrent marking algorithm that helps with making sure that the pauses in the concurrent marking phase, the pauses are small. The next one, of course, is something that you're all familiar with and comfortable with are the young collections. Young collections are similar to whatever you were used to before. So this is major change in not just the regionalized heap, but also the incremental compaction. Okay, so G1 has adaptive sizing, like I mentioned, and predictive logic. It's inbuilt into the algorithm, and that makes it very considerate to your pause time goals and frequency goals as well. What's interesting to know and remember is that your pause time has to be less than your frequency. So by default, the pause time is set to 200 milliseconds, and the frequency is set to your pause time goal plus 1. So it's 201 milliseconds. I don't have enough time to demonstrate, how tuning the frequency will change your application's response, because it tries to match your frequency goal as well. But what I have found is that if you keep the defaults as is, it works best. So you try to manipulate the frequency seconds. So I don't recommend changing the frequency goal unless you really think it's going to help you, okay? All right, let's talk about regionalized. So I don't recommend changing the frequency goal unless you really think it's going to help you, okay? All right, let's talk about regionalized heap. Did you have a question? No, okay. So in the past, you may have seen, if you have looked at hotspot GCs, you may have seen the same contiguous Java heap, but you would have seen regions. You will see the young generation, young generation, and then the old generation, and they'll talk about compaction and all those things. In G1, what I want you to do is forget all that and think of it as just regions here and there. Some of them are free and some of them are occupied. That's all G1 heap is about, free and occupied regions. And then what's important to know, the heap region size is always determined with the goal of 2048 regions. So depending on your heap size, G1 tries to achieve 2048 regions, okay? So the heap regions can range anywhere from 1 meg to 32 megs. They have to be a power of 2. The size, heap region size has to be a power of 2. And of course, heap regions are always aligned, okay? So if I put color to the previous drawing that I showed you, we have these occupied regions that are colorful here. And as you can see, some of them are Eden regions, some are survivors, some are old, some are humongous. So again, these are the generation does not have to be contiguous, okay? The only time you will see contiguous regions or you will need contiguous regions would be when you're allocating a humongous object, and I'll talk about that. So here it's in writing, the same thing that I mentioned earlier. Young regions are Eden and survivor spaces. Old regions are regions in the old generation. So basically when you have promoted objects, your live data set, your long-lived transients, they all go and occupy space in the old generation and out of the old regions. And then humongous regions are basically also allocated out of the old generation, but they're allocated into something known as humongous regions. Okay? So let's talk about what humongous means. So I'll use the same convention. We have the young generation region in blue, and we have the old generation region in green. So we have 3 different object sizes here. The first one is less than 50% of G1 region size. The second one is greater than or equal to 50% of G1 region size. And the third one is even bigger than a G1 region size. So what would G1 do? How would it allocate it on the heap? For the first one, since it's less than 50% of G1 region size, it is considered a normal object. So most allocations are out of the young generation, so this normal object will fall into that category and be allocated out of the young generation. The second object, which was greater than or equal to 50% of the region size, will be allocated out of the old generation into something known as humongous region, okay? And same goes for the third one, which is bigger than the region, so greater than or equal to 50%. But in this case, since it was bigger than the region itself, it needs 2 regions, and that's the only time G1 needs contiguous regions. So because it's trying to allocate an object that's bigger than the region. So the second object and the third object are humongous objects, and they need humongous regions. The first one is not a humongous object, so it needs the regular young generation, basically Eden allocation. So at the end, they will look like this. So these are old generation regions, and that's a region out of the young generation. We'll talk more about this during tuning, okay? I want to talk about the additional data structures, because this is something, again, because of the regionalized framework, these something new introduced. I mean, the concept has been there, trying to trace incoming references, right? But G1 now brings about remembered sets and collection sets, and I'll talk about that. So, like I said, these are additional data structures to help with maintenance and collection. If you had an application and you look and you know its footprint, you have to remember that because of these additional data structures, your footprint is going to increase, and I've seen up to about 5% increase in footprint. Okay. So let's talk about collection set. So when G1 is having an evacuation pause, it's going to have a number of regions in its collection set. So basically, that data structure will tell G1 what regions it needs to collect, and those regions will be collected. So anything that the CSET has identified, or anything that is identified in the CSET will be collected, okay? And as with any hotspot GC, young generation is always collected in its entirety. What that means is that the entire Eden will be evacuated and live objects will be either promoted into the old generation or they will be moved to survivor spaces. So, and that's the same for G1 as well. So a collection set for young collection will incorporate all the young regions. During a mixed collection, also known as incremental compaction, you again will have all the young regions, but this time you'll have a few selected old regions as well. What that means is that G1 will go through, during its concurrent marking phase, G1 will go through identifying the liveness per region and finding out how expensive it is to collect X number of regions, and those regions will, the better of the lot will be collected incrementally, okay? Based on the most garbage first. When I said better of the lot, which means that since compaction includes moving live objects to new regions, so you're compacting the live objects in a way. So, so if you have more garbage, the compaction cost is cheaper. So that's why you want to collect most garbage first. And that's the basic principle of G1, most garbage first. Okay, so your collection set, so if you take an example here, if you look at all the Eden regions and the survivor region, so during a young collection, that is what your collection set would look like. Okay, so it has all the regions out of the young generation. During a mixed collection, it will have all the regions of the young generation and only a few candidate regions. So it is not collecting all the old generation regions, it's only collecting the regions that it identified as regions that have. And we'll look at log outputs to see how. Oh, there you go. So the collection set, when you look at the, so another thing that has changed with JDK 9, Java 9, is the logging framework. So if you're used to print compilation log, or if you're used to print GC details, or print adaptive size policy, or even verbose GC, you know, those things have gone away now, and you use something like this. So you'll, for GC, you will use xlog GC, and then ergo, I want to trace. So I want to get most information out. So there are different levels. There's, at the end of this talk, I'll show you the JEP that talks about it. And this is how it looks, the log output looks with the logging enabled for Java 9. What I've identified here in green is the information about the collection set. So it says G1 finished, adding old regions to CSET. And then if you look at the next one, there were 13 old regions added. The maximum it could have added for that collection set were 68. So that's where the incremental compaction is. It's not using all the regions that are identified. It's only adding 13 old regions, because there's the prediction logic that, and there are other thresholds that I'll talk about soon, that tells it to only go up to 13. Don't use all the regions, because then if it uses all the regions it identified, then it becomes monolithic, right? We're talking about incremental, so at every collection it's only using a few of the old regions, and these are called the candidate regions. And we had more, yes? Yes, I will talk about that. Those are very important things, and it's a different concept, because we have incremental compaction, we have to have thresholds, and then these are there are defaults to these, and when you talk about tuning, we tune these defaults, but for most, the defaults should work. Okay, then something, moving on to remembered sets. Remembered sets are important because they track incoming references, okay? Since we are moving live data around, right, we need to figure out where we have moved, because there are other references that are pointing to the data that we're about to move, right? So, and what the good thing is, young generation is collected in its entirety. So we don't need to track young to young references. What we need to track are old to young references and old to old references. Okay. What is also new is the ability to have a more denser remembered set based on the popularity of a region. What that means is if you have an object that's popular, or if your entire region is popular because it's been compacted, it has a lot of live objects. So and all those objects are basically your cache, for example, that you're accessing once you've already built it up. So that region becomes popular, and eventually there's so many incoming references to it that the remembered set gets denser. So let's walk through an example. This example is taken from the Java Performance Companion book, and also the log outputs that I have shown here are from that book as well. So right now, there's a lot of information here, but what I want you to concentrate on is just region X right now. So region X is a young region. I could use my pointer if I know how to. Oh, there you go. Region X right here is a young region. It shows right here. And region X, so remembered set, there's one remembered set per region. So like we have seen here, there's one remembered set per region. So if you look at our set for region X, there's only one information is logged over there. And there's only one incoming reference as well. So the incoming reference is from region Z, which is an old region. So the incoming reference is an old to young reference. So that will be logged in our set for region X. Now if you move on to our set for region Y, there's an incoming reference from region X. Now this is a young region, so the incoming reference is from a young to an old region, but we don't need to log that because young generation is collected in its entirety. So they can be moved anyway. Then finally, region Z has two incoming references, one from region X, one from region Y. So now there's a young to old and old to old. But region Z, again, only has the information about the old to old reference. It does not log the young to old reference. So it's kind of simple like that. Kind of complicated, but that's the easiest explanation to it. Okay? So I was talking about the different granularities. So there is the sparse, that's where, so per region table, the PRT, is basically a housing. That's where all those things are kept. And based on the demands of popularity, the RSET's granularity changes. And the last one is a coarse grain bitmap, which has 1 bit per region. So it's really dense. Okay, and if you want to read more about this, you could refer the book or some online articles which I have in the reference section at the end of this presentation. So now I want to get more information. I have found out that remembered sets are a problem because my scan R set time is high, and since one of the reasons why your scan R set times could be higher is because your remembered set has become dense. So it's been coarsened, right? So we can use, so I'll go back again. So what you need to do, again, I'm looking at GC, and I'm looking at remembered set information, and I want to get as much detail as possible. And I have to enable unlock diagnostic VM option because our set trace is a VM diagnostic option. And I also want to make sure that I specify the period. And the reason you want to specify the period is if you don't do that, then it'll print it every pause. So every time you have a pause, you have a before and after our set information, and can get very complex to understand that. I'm only showing a part of the information here, and what I want you to take home is this right here. So if there was coarsening done, you would know it'll be noted right here. If there was some work, and since I'm not going into details, again, please refer those articles, but if there was some work done by your Java threads, you would know it here. If you ever see anything higher than 0, that is a bad scenario. And you don't want that to happen. So you want to let the concurrent refinement threads do their work and all the time. And you don't want your Java threads to be burdened with trying to figure out what the incoming references are, right? Because that's the GC's job, not the Java thread's job. But it could happen, and there's a lot of tuning we can do about it. Again, not going to cover it here, but please go read those online articles and the book, or, you know, there's a lot of information out there that I've contributed to. And then the process cards. These are the same cards that we know about, the card table, so it's the same thing. So let's talk about G1 GC phases. And the first one is the Young collection. Again, this familiar diagram. So we have the Eden and Survivor regions identified in our collection set. Once the collection happens, you will see the live objects are either moved to the survivor space, a new region here, or some of the objects are promoted. So again, all the regions are identified, and after the collection, this is called the compaction, the young generation compaction. So all live objects are moved. If you wanted to see more details of what's happening during your pause, again with Java 9, you will have to use phases, because I want to see the phases, and equal to debug. So I want to get more details. And it looks like this, crazy. It's pretty intimidating, and it goes on. This is just one pause information, okay? And what I want you to know is that if you ever looked at G1 before Java 9, it's the same information. So if I had enabled print GC details with my Java 8, the information is similar, okay? And let's look at this, because this is probably what everybody else is used to. So let's look at that. The first information that's printed is your type of pause, and then the cause of pause. So it was an evacuation pause, that was the cause, and the type is young collection, okay? And how much time it took. So we'll talk about that too. And then it talks about the parallel time. So in G1, we have something known as the parallel phase, and then it's followed by sequential phase. There can be multiple threads employed in both of them. The only important thing to know is that the sequential phase cannot means that it has to happen one after the other. The parallel phase has 8 threads, GC worker threads, and these threads are similar to what you may be used to, the parallel GC threads, okay? If you want to change it, you use the parallel GC threads option. And I'm not, again, there's a lot of information online. Please go and check that. I have links again at the end, so for that. But what I need to differentiate here, sequential phase out. So there's a indentation, and you see that, so parallel time right there, and then you have the sequential time right there. So the sequential phases, so first the code root fix-up happens. That's basically simple code root, the root, simple root. And then there's the clear card table. And then if you look at the other time, that's where G1 does other work, like whatever's left over, so to speak. In this particular case, I wanted to highlight something known as the humongous reclaim. In JDK 8 update 40, you could now reclaim dead humongous objects. Prior to JDK 8 update 40, if you had a dead humongous object, or humongous region in your old generation occupying space, it's dead. It's not doing anything, it's occupying space. It will not be collected until a cleanup pause. But that means that it counts towards your occupancy, heap occupancy, and it could lead to evacuation failures, because G1 doesn't have any more regions free, right? Because this thing is occupying space. But with JDK 8 update 40, you would see something as humongous reclaim, and if you did have a humongous reclaim, it'll show up in the time here. Eden space, what was the Eden size before and after, and what's the new Eden size, survivor sizes, your total heap size, and then the times. What usually it's helpful to me to plot the user in the real time to see the scaling. So I had 8 GC threads. I want to make sure that that's what I'm getting. So that helps me with scaling. But that's just performance tuning. It doesn't have anything to do with GC. With G1 here is plotting it. And the reason I'm doing that is because this drives me insane. This is in Java 9. Let me just go back quickly. Look at that. This is all this crazy information. I don't need all that information. What I need to know is if my external root scanning time was all right, my update RS, my scan RS. So all those things, I just pick and choose. I make my own parser, and I plot them using JFreeChart right there. And here I can clearly tell that everything looks okay, right? What you see in red is your actual pause time, okay? The maximum I can see here is 70 milliseconds, way less than what I had specified. I think man was 80. This is a simple run. It's a benchmark, so. And what I see right below that in blue is your parallel time, which is awesome because that means that most of my time was done in parallel activities, which is great. And right below that in light blue is your object copy time right here. See, object copy time is light blue, and there's your light blue line here. And again, this is great because most of your pause should be what? Should be object copying. Your live data should be compacting. That should be a pause. You shouldn't be spending time in code root fix-up or other time or clearing card tables. Most of the time should be object copy. So if you have live data, that needs to be compacted. So that's what it should be. So most of my time is object copying. Now, if I would have seen any of these lines here to be higher, maybe 20, above 20, more than 10% of the pause, or something like that, and I would be worried. But right now it looks okay. So this is a great visual help for me, and I don't have to dig into. And then eventually, why is this high? So I'll go look at the pause times and see my scan RS times. Why is that particular thing high if it was continuing to be like that? So moving on to marking threshold. So now we have done the young collections. We have aged our objects, and we have promoted objects into the old generation. We need to start collecting the old generations, otherwise we'll have evacuation failures, right? No more space in the old generation. To be able to start collecting dead objects from the old generation, we have to cross something called marking threshold. In Java 9, the marking threshold is adaptive. Prior to Java 9, the marking threshold was fixed at 45% of your heap. Marking threshold in G1 GC is called initiating heap occupancy percent, which I called IHOP. Simple, easier to remember. So it's a threshold to start the concurrent marking cycle, and that's when all your live objects are identified. All of the live objects, not just a certain number, but the entire heap will be marked, basically. When old generation occupancy, or actually your heap occupancy, crosses this adaptive threshold, the concurrent marking cycle will start. And it's based on the total heap size. So let's look at the concurrent marking stages. The first one is called the initial mark phase, where it marks all the root objects. So if you remember, a young generation is also start the world, also identifies root objects. So what's easiest in this for this particular phase is to club it with young generation, which is known as piggybacking. So it happens at the same time as your young collection, and marks all the roots. Now, after a young collection, what happens is we have objects in the survivor space. So we have started marking the roots, but remember, we did not do anything with the objects that survived, right? So this particular thing is called in the survivor spaces are known as the root objects also. So this is what is done, and you can do that concurrently because it doesn't need stop the world. You already know the objects that just got promoted into the survivor spaces. You just mark them as roots, okay? But it must complete before the next GC pause, because remember, we are considering the survivor regions also as root regions. So we need the information before we can do a pause, next any young collection pause, okay? And now that we have identified the root regions and the root objects, we need to start our marking. And that's what happens during concurrent marking stage. It's concurrent and and then time, and that's when you look at the concurrent GC threads count. It's 1/4 of your parallel GC threads, I think. Number of processors or number of threads, that, and kind of helps your application, kind of helps the GC. It does have a pre-write barrier, and there's live data accounting done during the. And what's really important to know now is that I think some JDK 8 update, now we have class unloading with concurrent marking. This has been a very useful option for CMS. G1 didn't have it for a while, and with some JDK 8 update, now G1 has it on by default. So your class unloading can happen during concurrent marking. The final mark, also known as remark, it stopped the world. So your application was working while you were marking, and some objects may have been missed. So you cannot claim that you have done live data accounting if you have missed some live objects. And that's a big no-no. That's a GC error, right? GC just missed some live objects, so it's a wrong algorithm. So in order to make sure the algorithm is correct, we need to have a stop the world pause, and that time you traverse any unvisited live objects and complete live data accounting for your entire heap. Also, reference processing happens during the parallel GC threads. Reference processing is high. I recommend please use that option, so it'll use parallel threads to process all the references, no, reference processing. So references like final or soft references or whatever. So, and then cleanup. So why do we need cleanup? We have our sets that we had during the collections, right? So we need to scrub that. Our live, so we have an idea of our live objects in the old generation. The regions with the most garbage. And how do we know what regions have most garbage? We do accounting. So that regions to the free list. So remember, we collected and compacted regions. So there are a lot of free regions. We move that to the free list. So that's done concurrently. So during cleanup, I had mentioned this before, if cleanup finds any old region that's completely full of garbage, it can be reclaimed. So in this particular case, it identified that that particular old region is full of garbage, and it was reclaimed. So remember, prior to JDK 8 update 40, that's the only way humongous objects could be reclaimed. I mean, there's another way, of course, full compacting GC, which you want to avoid anyway. So this is the only time it will be collected. I want to find out more details on concurrent markings in JDK 9, so I will go ergo, which means give me any and every information, which is also equivalent to what you may be used to. It's called print adaptive size policy. So if you're used to looking at print adaptive size policy information prior to JDK 9, you want to use ergo now, and this is how it looks. Very pretty. So what we see here is initial mark right there, identified in blue right here. And then it tells you the number of regions that it worked with during that initial mark pause. And then right here, you see how much time it took right here. Then you see the other phases. You see the concurrent root region, concurrent mark, pause remark, pause cleanup, concurrent cleanup. So remember the stages that I showed earlier, that's all seen here. Okay. So if this was your heap configuration, this I have shown before when I was talking about the C sets for mixed regions, right? All your young regions are candidate regions, and a few selected old regions are candidate regions for mixed collection. And that's how pretty your heap looks after mixed collection is done. I want to find out more information on mixed collection. I want to use the ergo option with even more information, which is the trace. Again, print adaptive size policy and print GC details prior to Java 9 would give you the same information. Again, very pretty. This is your mix, that's where your mixed collection started. It started choosing collection sets, so I'm not going to go into details because I'll go into each line later. And that's the last of it. It took 47.5 to 9 milliseconds, okay? Same thing highlighted. Okay, so this was the next line that I was talking about earlier. So this is where you see add young regions to C set. So it added 179 regions. The prediction logic that I was talking about. The predicted time 2 milliseconds. My target was only 50 milliseconds. So it's predicting that it's going to take more time than my target. The next line says that the prediction time is 0.77, and now anything that is going to add is going to be expensive, remember, because my time was only 50, my requested time was only 50 milliseconds, and it was already over that during the young collection set. Now it's adding some old regions because I have the minimum and maximum threshold, right, for the old regions, so it has to add those regions no matter what, because based on my thresholds. So now it's predicting even more expensive. So basically it's 76 plus 14 now. And anyway, so this is how the prediction logic works. Again, it's not hard real time, so it's not stopping my collection once it passes. It's still going to collect the regions it has to collect based on my defaults and my thresholds, but it keeps on telling you, hey, this is a problem. I'm predicting that it's going to take more time. And I think it did take a long time. Let me go back. No, it didn't. So prediction logic was wrong. So it's only 47 milliseconds, which was less than what I had asked it to give it. Okay, so what do I do with the I don't need to look at that information unless I really find something of interest. So all that information that I said earlier, so that's your young collections right here. Pretty good. Less than what I want. My time, I think, was 50 or whatever. So this is your initial mark. Again, almost 50. I'm happy so far. This guy over here is another young collection that happened. I may want to investigate that, and that's when I will go back to the trace and look at what happened during that pause. This right here, remark, again, a little bit more expensive than what I expected. Maybe reference processing is the problem. So again, I'll look at the details and see how much time reference processing took. Okay? Right next to the remark is your cleanup. Pretty good. Another young pause, this is where it identifies the regions and sorts them right here. And then this 1, 2, 3, 4, 5, 6, 7, these are your incremental compaction. So at the beginning, it identifies how many old regions it needs to collect based on the reclaimable percentage, and I'll talk about that here. And it does those incremental compactions right here. And you see the last one is so expensive. And it's expensive because my thresholds were not set correctly. So now I need to go and adjust my thresholds, which we'll talk about next. It's expensive because it's collecting more live regions with more live objects. Okay. So now tuning. So the goal is, for everybody, is to let the GC ergonomics. The GC ergonomics is a word coined by Hotspot GC team. So basically, it's the stuff that happens with respect to your GC based on your system. Defaults, lots of thresholds. You want the garbage collector to do its job, okay? If it's not working the way you want it to be, then there are 3 things that I would recommend. Of course, your pause time goal. Maybe you are putting too much pressure on G1. So maybe work with that. Make sure your information is able to be contained in your old generation. So your heap sizing is important. Your threads, concurrent worker threads and parallel worker threads, maybe you want to employ more if you have the ability. Tame mixed collections. Remember the last one I showed you, the 7th collection was very expensive, and I may not want that. So I can work with kind of changing the thresholds for that. Avoid evacuations, failures, of course. Make sure that you're collecting enough so that you don't run into no space, right? So, okay. So, okay, cool. So these are the thresholds, very important. These slides will be available to you guys, so even if I don't reach the end, these thresholds will go home with you, I guess. So, mixed count target is the maximum number of GCs that can happen, incremental compaction. So the target defaults to 8. In my case, I only went up to 7 based on other thresholds. This sets the minimum number of regions that you have to collect. So even if G1 predicts that it's an expensive collection, it still has to collect the regions that so right there. See, old CC minimum, which means that because that's the G1, that's the algorithm default, and I can change it. If you change that option, you can change this. Next one, this one is for the maximum that you can collect. If you think you're not collecting enough during each incremental compaction, you can change this option right here, and then you can collect more old regions, okay? And then it shows, see, it shows old regions 45 right there, you know, because that was the maximum I could collect. G1 heap waste percent, that's the amount. So if I know that most of my old generation is going to be live data, and it's about, say, 5 to 10% of my heap, I can use that to my advantage here. And that's what you see here in reclaimable threshold. So I have 8% to be reclaimed, and my threshold is 5. So anything below 5 will never be reclaimed. It won't be touched. So if my heap has like anything that is like 5% or less reclaimable, it won't be touched. So it'll stay in your heap forever. Mixed GC live threshold percent. So each region has a threshold, like if I'm having, my region is 100% occupied, of course, and if I have 80% live or 85, in this case the default is 85, if I have 85% live, then it won't be a candidate. It's too expensive. G1 will not touch it again. It shows right here in the candidate old regions. And I was going to talk about promotion failures. This is evacuation failure. It'll show up in your log just like this, evacuation failure. And it shows up here in the tags as 2 space exhausted. It tells you how much time it took for during the evacuation failure. Evacuation failure is very expensive, and it happens because you have no more free space to promote objects to. It could happen in survivor regions. It could happen, of course, it happens mostly in old regions. Okay, great advices here. A heavily tuned JVM command line option could be an issue. So start just with your basic heap sizes and your pause time goal. Let G1 do its job and see where it gets you. Of course, this is not just for G1. If you don't size your heap to accommodate your live data set and your transient long-lived, then you have a problem, right? Because even for monolithic compaction, where is it going to compact to, right? If you don't size your generations, do not accommodate that in your old generation, it's going to end up going back-to-back reclamation, and that's a problem anyway. So please size your heap accordingly. And your thresholds, your marking threshold. If you don't start your marking on time, that's a problem. So start your marking on time. Right? And then same thing, if it's marking cycle is taking, you started it on time, but it's taking a long time, add more concurrent threads, okay? Or reduce the threshold even further, start it earlier, okay? Okay, this is good. Fragmentation. Okay, so quickly, I'm not going to talk about these fragments. These are internal fragmentations. But something that's really important to know is the humongous objects waste space as well, right? And that's internal fragmentation as well. And so the goal is that your humongous objects are few in number and are short-lived, right? But if you have a lot of long-lived humongous objects, you can have evacuation failures, right? And then you have external fragmentation if those objects are just there and you can't find contiguous regions now. So you have these objects, and now you have other objects, the normal objects that got promoted, and now a new humongous objects comes along. It needs a contiguous region, can't find it, even though there are regions. So you have free regions, but not contiguous free regions, and that's the problem. So now you have an external fragmentation. So keep that in mind. This is how you can use the ergo information to find out about humongous objects right here. Humongous regions, humongous object allocations. Summary, know your defaults, first of all. Always know your defaults. Understand, for example, we know about the region size, so we can find out what the humongous objects are. Great, I've already spoken about all those things. We spoke about taming mixed GCs, the marking threshold, your liveness in your garbage. Okay, please go ahead and read it, okay? And this is what I was talking about. There's a lot of information that I've contributed to. Please go ahead and read all those. Ask me questions if you have. This is the hotspot GCUs if you are using the garbage collector, any garbage collector. If you're developing or working with the garbage collector, please go ahead and ask questions on these two areas. This is me. Go ahead and ask me questions too. And then that's my Twitter handle. And that's it. Cool. Thank you.